Okay, so this is section 2.3, day 2, video 2. So last time we started talking about some of the rules. We started talking about the product and the quotient rule. We already know what the power rule is. So the thing I want to go over with today, or in this specific lesson, is that you don't always need to use a quotient rule just because something looks like it's a quotient. And then we're actually going to talk about some higher order derivatives, which just means derivatives of derivatives and then some of the meaning there. So let's go ahead and take a look at some of these problems. And like I just said, not every quotient needs to be differentiated by the quotient rule. In some cases, it's actually going to be more convenient to use a power rule. And you might look at some of these and say, well, they look like quotients. You can still use the quotient rule, but it's probably not going to be the most efficient way. So, for example, number one, or the first one there, is x cubed plus 2x all divided by 6. So what we can do is we can actually split the numerator over a common denominator. So we can write this as x cubed over 6 plus 2x over 6. So basically all we're doing is we're taking the process of combining fractions and splitting it up. We're going backwards. And the reason that we're going to do that is because x cubed over 6 is the same thing as 1/6 of x cubed. Okay, it means exactly the same thing. And 2x over 6, the 2 and the 6 can reduce to 1/3, so that's the same thing as 1/3 x. From here, this is much easier to take a derivative. So now, y prime, using the power rule, we bring the 3 out to the front, multiply it by the 1/6, so 3/6 is a half. Reduce the power by 1. And then the derivative of 1/3 x is just 1/3. And that's it. Okay, probably much shorter, much easier, and it's already simplified than trying to do the quotient rule. Could you have done the quotient rule? Sure. Just remember that when you take the derivative of 6, it's 0. So when you multiply, times the top or whatever, just remember that you would need to do that. Okay, same idea here in the second one. Instead of trying to take a quotient rule here, I'm going to rewrite this as 3/7 x to the 6th. Much easier to take a derivative now. So y prime, bring the 6 out to the front and multiply it. So 3 times 6 is 18. So 18/7 x to the 5th power now. Again, no need to do a quotient rule there. Biggest thing is going to be recognizing when you do and when you don't need to use a quotient rule. Now you might look at the next one and say, oh, well, that one definitely looks like a quotient rule. Well, one way or the other, even if it does, you're going to want to distribute that -3 on the top first. So we're going to get -12x plus 15x cubed over 7x squared. But again, the denominator here is one term. It's going to be much easier algebraically, in my opinion, to go ahead and split this thing up over the denominator and then reduce. Now, I'm going to do all of that in one step here, so hopefully you can follow this. So we're going to get a -12/7 from the first one, and then x over x squared is going to reduce to a 1 over x, but the x will be left in the denominator, so when we bring it to the top, we make it x to the -1 power. And then 15x cubed over 7x squared, the 15 over 7 doesn't reduce, x cubed over x squared just becomes x. Now we're ready to use our power rule. Again, much, much easier from here. So let's see, bring the -1 out front, multiply it by the -12/7. We get 12/7 x, and that will now be to the -2, subtracting 1. And then the derivative of 15/7 x is just 15/7. Done. All right, next one down. So it looks like I can reduce the 18 over 6 simply to 3 on the top over x to the 4/3. And then remember, I want to bring that up to the top. So when we bring it up to the top, it's going to be 3x to the -4/3. And now we're ready to go ahead and take our derivative. So y prime, bringing the -4/3 out to the front. -4/3 times 3 is -4. X, Subtracting 1 from negative 4/3 is subtracting 3/3, so we should get negative 7/3 as our new power. And there you go. Again, you didn't need to have to do a quotient rule and all those because a lot of those algebraically simplify first. So you should probably try to look for that first. If you can't, the quotient rule will work. Okay, so let's go ahead now and talk about higher order derivatives and what it means to be a higher order derivative. So we already know that we can obtain the velocity function by differentiating or taking a derivative of position. And that's because the velocity is the rate of change of position. It's how the position changes over time. That's why the velocity or a slope is a slope of position or the derivative of position. Likewise, we can obtain acceleration by differentiating velocity. Because the acceleration is actually the rate of change of the velocity. It's how is my velocity changing over time. That's what acceleration is. So another way of looking at this is that we can obtain the acceleration function by differentiating a position function twice. So if we were given a position function, we could actually find the acceleration by taking the derivative of position twice. You'd have to get the velocity to get to the acceleration, but that's the general idea. There's a higher order derivative, two derivatives. So S of t represents position. I am not really sure why S has been used for position, but it is. V of t, which is your velocity, is the same thing as the derivative of S. And then A of t, which is the acceleration at time t, is the first derivative of velocity or the second derivative of position. They are the same thing. That's acceleration. Okay, a lot of people call this PVA, position, velocity, acceleration, because that's the order it goes in for derivatives, if that helps. All right, so the function given by A of t is the second derivative of position, which is S of t, and is denoted by S double prime of t. That's the double prime. It almost looks like quotation marks there. It's actually called double prime. That's just the way it's said, S double prime of t. So the second derivative is an example of a higher order derivative. The third derivative is actually going to be the derivative of the second derivative. And in terms of the application of physics here, the third derivative is actually what is known as the jerk. And the best thing that I can do to kind of give you an example of that is if you were to think about like a whip. I don't know if you've seen it, but if you like crack a whip and you actually throw the whip out and then you snap it back, when you're snapping the whip back, it's actually jerking the acceleration in the opposite direction. That's one way. Another thing you could think about where you might see jerk in actual action is if you've ever seen somebody parachute and you're watching them fall, as soon as they hit their parachute and the wind hits it, they kind of have this upward motion. It actually is taking the acceleration and jerking it back in the other direction. There's probably several other examples, but those are probably the two of the easiest or most common ones I can think of. All right, so higher order derivative notation. The first derivative is given, and we've seen that, y prime, f prime. We haven't really used this dy over dx notation that much yet, but we have used it a little bit. Or the d over dx of f of x, we will see that. You probably will not see that one very much at all. The second derivative then is going to be denoted with a double prime, so two prime symbols. So y double prime, f double prime. When you go to the dy over dx notation, the 2 actually goes in between the d and the y on the top, and then after the x on the bottom. There is a reason for that. It's probably not something we're really going to go into. If you happen to take Calc 3, you'll actually understand why this is that notation. But that's the notation. So if you see that, it just means second derivative. Same idea here, because you can technically pull the y off to the side and call it f of x. Third derivative, triple prime notation, okay? And again, the 3 goes after the y, after the d, and then on the bottom it goes after the x. Notice what happens when we get to the fourth derivative. The fourth derivative does not keep using prime symbols because that would actually get very long and drawn out, and it actually becomes much more difficult to figure out, especially if you had to start counting up all the primes to figure out where you're at. So what they do is they just use an actual number. Now, the biggest thing here is you can't leave the number. If all I was to do was write this, that would indicate y to the fourth. Notice the difference here is that they put a parentheses around it. Now that indicates a derivative. It's not y to the fourth, it's the fourth derivative of y. So that's the major difference. So again, a fourth derivative looks like this. The dy over dx notation still uses a number in there, just like it would for all the rest of them. So you can do an nth derivative. We could do the 17th derivative or the 27th derivative or 51st derivative or whatever. So you would just replace that number for the n, and that would be the derivative you're looking for. Okay, so actually let's go ahead and do one application, and then we'll be done. It will take us a little bit longer to get through this because of the graphs. All right, so the position function, or excuse me, the position of a particle is given by the equation s, which is our function of t, which is t cubed minus 6t squared plus 9t. So that gives us the position of the particle. If we were to plug in 7 for t, that would be, okay, at 7 seconds, that's where the particle is of this specific, wherever this thing is. Usually it's on a straight line or something, but this does not look like it's on a straight line. We want to find the acceleration of this particle at time t. Well, to find the acceleration, we need the second derivative of position. So let's go ahead and find that. To get the second derivative, we need the first derivative. So the first derivative looks like it is 3t squared minus 12t plus 9. And don't forget that first derivative is the same thing as velocity. That's the derivative of position. But what we want is the acceleration, which is the second derivative of position. So that's going to be the derivative of what we just got. So that looks like that's going to be 6t minus 12, which is the same thing as v prime, because it's the derivative of velocity, which is our acceleration. So we have just found the acceleration function, which is 6t minus 12. So now all we want to do is say, okay, what if we want the acceleration after 4 seconds? We just plug in 4. So a of 4 is going to be 6 times 4 is 24 minus 12 is 12. So it's 12. And the units are meters per second. That would be velocity per second, because it's how is the velocity changing over time. And we typically write that as meters per second squared, okay, because it's 2 derivatives of time, okay, 2 changes of time. That's why the second part is squared. All right, so we can actually take a look. I'm going to do my best to sketch this. We'll see how this goes. We'll kind of sketch what these graphs look like, and then we're going to talk a little bit about speed right at the end, and we'll be done. So let's go ahead and take a look at this. So we want to graph the position, velocity, and acceleration functions from 0 to 5. So let's go ahead and mark 1, 2, 3, 4, 5. So each one of those is worth 5 units. And this is going to be a really rough sketch. I'm not doing all the specifics on here, but let's see. So I know that the position of the particle is t cubed minus 6t plus 9. So the position function actually looks something like this. And this is a sketch. So if you really wanted it more accurate, you're going to plug a whole bunch of values and stuff in. But this is what this one looks like. And again, we're only going from 0 to 5, so I don't have to go any further than that. So it's going to start here at 0, because at time 0, that's position. It's going to go up to right about here, start to come back down at 3, and then start to go back up again. And I don't exactly know where it stops, but it stops someplace at 5. Now the velocity, which is, let's scroll back up here, the velocity is 3t squared minus 12t plus 9. That's a quadratic, so we know the shape of a quadratic should look like a parabola. And from 0 to 5, so at time 0, that's going to be at 9. Let's switch colors here. So it's going to hit up here somewhere. And then it's actually going to come down this way, cross through the x-axis at 1. I missed 1. Bottom out at 2. Cross back through the x-axis again at 3, and then continue to go up. And it's going to stop at 5. I'll just put the arrow there because I'm not going to be able to hold the way to 5 on my... All right, and I should probably label that this was my position function. All right, and my sketches are not the best. I'm trying to do my best here, but let's see. Let's go with orange for the acceleration. The acceleration function is a line, 6t minus 12. So it's going to have its y-intercept way down at -12, and it's going to have a slope of 6. So the y-intercept is going to be like way down here. And then it's going to have a slope of 6. So it's actually going to come up, go right through x equals 2, and then keep on going. So one of the things, and we've talked about this when we talked about the graphs, one of the things you should see is the position function is the blue one. The position has a positive slope right up until it gets to, let's go with green, right up until it gets to here. Well, what you can see, and my graph is actually not the best, because actually it should have been more like over here before it started coming down. All the values of the derivative are above the x-axis. So my position function is definitely not drawn well. If you plug all these things in your calculator, you'll actually see it because it'll graph it much better. So really, let's just try and fix this. This thing should have started coming down much faster, like this. Something more like that. Okay, a little bit better. And then the function, and then the blue function starts to decrease after the green dot, and you can see that all the values where it's decreasing are below for the red one. The red curve is below the x-axis, and you can see that right there. Whoops, probably should have done that in green. Wow, that's supposed to be green. What's going on? There we go. And then the blue curve starts to increase again, so it's got positive slopes, and all of the red stuff is above the x-axis. And then you can kind of look at the red one as well and say, okay, my red function is decreasing from here to here. And as you can see, I actually did this one pretty well. All of the orange values are below the x-axis because they are negative slope values. And then the function on the red line, a red curve, starts to go back up, and then all of the orange stuff is above the x-axis. Again, this is something which is really important for you to be able to piece these things together, and we'll do a lot more practice of it, but if you're getting it, then you're right on point. If not, we need to keep working at it. All right, last thing we're going to talk about, and it's good that we have these graphs up here, we're going to talk about the speed. Okay, when is a particle speeding up? A lot of people confuse speed with acceleration. They are not the same thing. Speed is actually the speed itself is the absolute value of velocity. So it has nothing to do with what direction you're moving in. It's just whatever that velocity is. So the idea of speed is, if you want to know when something is speeding up, the velocity and the acceleration have to be working in the same direction. In other words, both of them have to either be positive or both of them have to be negative. So if your acceleration is positive, meaning you're moving forward, but if your velocity is positive, meaning you're moving forward, but your acceleration is negative, it's like you're moving forward, but you're hitting the brake. The acceleration and velocity are working against each other, which is why when you're moving forward and you hit the brake, you start to slow down, because the acceleration and velocity are against each other. However, if you're moving forward and you hit the gas pedal, now you're moving forward and your acceleration is positive, meaning that you're speeding up. I kind of hope that that analogy helps to make sense a little bit. So the idea is, for something to be speeding up, velocity and acceleration must be the same sign. And for something to be slowing down, velocity and acceleration must be opposite in sign. So one will be positive, one will be negative, and it doesn't matter which one. So let's look at our graph. According to our graph here, when is the particle speeding up? Well, we want to know where on the graph the velocity and the acceleration are doing the same thing, are in the same positive or negative. Well, the velocity is the red, and the acceleration, which I forgot to label, was the orange. So where are the red and the orange the same? Well, it looks like both the red and the orange are the same between here and here, because they're both underneath the x-axis. And then they're both above the x-axis after time 3. So it looks like between times 1 and 2, and then after time 3. And we're only going to 5 because that's where our limit is. So it looks like from time 1 to time 2, also from time 3 to time 5. And we can actually put a solid bracket on 5 because this thing stops at 5, and at 5 it's still doing whatever it did before. Technically, if we didn't stop at 5, that last entry would be an infinity. It would go on forever. So then when would the particle be slowing down? Well, velocity and acceleration have to be opposite in sign. So it looks like from 0 to 1, your red is above and your orange is below the x-axis, so they're working against each other. So from 0 to 1. And then it also looks like from 2 to 3, so in between 2 and 3, the red is below and the orange is above. So they're working against each other. And notice that there are parentheses on all of them except for the endpoints here. And that's because when they actually hit those specific marks, one of the velocity or acceleration functions is 0, so there's technically no sign there. So we can't really include those points. There's actually some debate about that in the calculus world, but for now we're just going to go with open parentheses, only close parentheses on the endpoints in this case. All right, that is plenty enough. You should have enough to get everything done, and I hope that was useful.